When I first started writing this presentation 3 years ago, very few people were actually talking about how to test AI. They were talking about using AI, they were talking about using it in testing and how we weren't going to need testers anymore because it would do all that for us. But no one was actually talking about how do we test AI itself. So, I've had to rewrite this multiple times in the last 3 years because everything moves so quickly. And I'm sure that a lot of what I talk about, you'll have already heard bits and pieces of it, if not all of it. But it's a case of pulling this together so that I can give you a toolkit that you can use right now to start testing AI-based systems. But bear in mind, there are more AI systems than just LLMs. The large language models are not everything. There are lots of others as well out there. So I'm going to be talking pretty quick to whiz through all the information because there's a lot of stuff in here. So how do we test AI? Well, I've got some good news and some bad news. The good news is the test levels look pretty similar for testing AI to the stuff that we've been doing for years and years. Also, AI has been around for a long time. There have been non-deterministic systems in live being used by, for instance, the financial industry for a long time. So some of this stuff is very well established, and you can find it out there if you know what you're looking for. The bad news is you're going to have to learn some new skills, going back to what Tariq was talking about this morning. But I think that's good news because I'm permanently curious and a learnaholic, so that's good news as far as I'm concerned. But there is some specific challenges when it comes to testing AI because of the nature of AI systems themselves. So first up, we have the oracle problem. So because it's non-deterministic, the answers it's giving are probabilistic. It means that we don't have expected results in the same way that we used to. We can't say pass, fail because it said a precise number or something specific happened, which makes it quite difficult for us. Also, the code is not the algorithm. The data, past and present, is. And that data, generally speaking, is in very large quantities and can be quite complex. It's what AI is good at, is sifting through vast volumes of data and finding patterns. And because the data affects the behavior of the system, systems tend to be self-optimizing. They change, they evolve. And that we wouldn't actually use AI systems for doing simple tasks. It's pointless. The tasks that we give it are actually quite complex, and as such, we have complex systems. And a lot of those tasks that we ask it to do are essentially mimicking human behavior. And human behavior, by its nature, is actually very difficult to define exactly. And then there's the problems of bias. We've heard a lot about that recently, and I'm sure that you've all seen some of the problems that have occurred in live with bias problems. And we have bias in humans, never mind in AI systems. And then we have the hallucination, or more accurately, the confabulation, which is quite a mouthful, but it's more accurate to talk about confabulation, which is where you have a premise that there is an answer, and even if there isn't an answer, the AI system will find an answer to fit the pattern, even if it's complete rubbish. And then, how do we know we've tested it enough? How do we measure the test coverage? It doesn't really fit in the same sort of ways. You can't do code coverage, it doesn't make sense. And you can't refer back to the requirements in the same sort of way. because you don't have a clear requirement. So, what are the test levels that I mentioned that are familiar? So we have unit or component, integration test, and end-to-end testing. All sounds very familiar to us, doesn't it? And then UAT. We all love UAT, don't we? But the less familiar ones, model testing, which is what most people think of as actual AI testing, data testing, and monitoring in live. A lot of people consider that not to be a test level, but it fits really nicely with the DevOps philosophy of shift right. And it's very important. And Tariq mentioned that one this morning as well in his when he was talking about quality engineering. So, first one up, component test. Now, traditionally, this is either black box against the requirements or white box against the code. But neither of those make very much sense. But every single AI system has to have a data feed. That is what actually makes it work, the data. So we can test those data feeds in and out. And that's where we apply the skills that we all know. Field validation, in effect. So that we can test whether it can handle false zeros, whether it handles dirty data, blanks, nulls, duplications, all those sort of things. And if there's any sort of transformation that goes on or normalization of that data when it's fed in, is that being done correctly? This is something that tends to get overlooked a lot because it's generally thought that all you have to do is throw the data at the system and it'll handle it. And there's a lot of work that has to be done up front to make that data suitable. And we can point out where it's not. And that leads nicely into data testing. So, because the code is not the algorithm, we need to be very aware of the data that we're using within it. And that needs to be tested. And this is where we get some new skills that we have to consider, because we have to think about the different areas. Now, the experts in this are the data scientists. So what we want to do is cozy up to the data scientists, learn some of their skills, but we don't want to take the job away from them. We should use them. We should get them to do all the hard legwork for us, and we ask the awkward questions. So what should we be asking questions about? Well, first off, bias and fairness. As I said, we know about the bias problems, but you also have to consider other factors within that bias, like proxies for bias. These proxies can be things like jobs. There are very few male nursery nurses, so that job is a proxy for gender. Likewise, address can be a proxy for bias. So that can be a proxy for race, income, status, even age. Now, sex, age, and income, and race are all things that, if a decision is based on that, then that's discrimination. But we do have to make sure that the data that we're using is diverse and appropriately diverse and covers all different options, including edge cases. But it has to be representative of what we're testing. For instance, the facial recognition system that was trained in California isn't necessarily going to be suitable everywhere in the world, as has been demonstrated to some people's cost. Also, part of the process is actually labeling, annotating the data, so putting it into categories. If those categories are too granular or not granular enough, that causes severe problems with the categorization of the data. And so you get the wrong answers out. And then data splitting. It's usual to take a massive data set and then use 80% of it for training data and 20% for the testing data. But you need to make sure, again, that the bias isn't there, that the representativeness of it is, so that the testing data and the training data are representative. Both sets are representative. And this is done through statistical analysis. So as I say, you want to find your friendly neighborhood data scientist and get friendly with them, because they are our friends. That's the future. Us understanding data science so we can ask the awkward questions, the ones that people don't like us asking, that get the answers that we want to hear. And to do that, we need to understand data science. So, next level, integration test. Again, it's familiar, but because the systems are probabilistic, when you chain those in an integration, the error factors multiply. So if it's outputting probabilities of it being a cat, dog, or a blueberry muffin, and then you want to identify those dogs, it's going to have problems there. You have to watch out for those error factors multiplying. An example of this is facial recognition. First, you have to recognize that it is a face, and then feed that in to recognize whose face it is. And as you can see, facial recognition for something as simple as a chihuahua isn't that simple. Model testing, as I say, this is what people consider it to be AI testing. It's statistical in nature, and it's done by feeding very large volumes of data in and then analyzing how it behaves. This tends to be complex to interpret because the data itself is usually unstructured and we just push it through. So again, we want to talk nicely to our friendly data scientists. But our job is knowing what questions to ask, because data scientists are just as likely to be biased in the way that they think about the data as the system is. So we've got to spot that. We've got to ask those awkward questions again. Here's an example of some statistical analysis we did on a synthetic data generator that we use for generating test data. This was way back in the early days, so this was early test runs. And you can see it's comparing the data that we're trying to emulate with the synthetic data. And you can see the differences. They spot quite easily. And again, more categorizations of the same data compared together. So this is a simple statistical analysis that immediately gives you an answer. You can see it doesn't match. And there, it's even more obvious. You can see the spikes in the data. It's not representative. So you can use these sort of techniques for both data testing and model testing. And then we come on to end-to-end. Now this is very familiar, but again, beware of that complexity, the fact that the error factors multiply. And if your overall system is designed to be an expert system, emulating expert behavior, then use an expert to test it, because they're the ones that are going to be able to point it out if it's not working. And then the one we all know and love, UAT. Very familiar, but watch out for automation bias. This is the propensity of humans to prefer the output from an automated decision-making system. It doesn't even have to be AI, but they'll prefer that over a human, even if the automated system is completely wrong and the human is completely right. It's a classic case of the computer says now and then believing the computer. Let me come to the last one, monitoring live. This is essentially monitoring the performance of the system, but performance isn't just speed and volume. It's also accuracy. And this is critical, absolutely critical to the quality of what you're doing. For instance, if you've got an AI system that's spotting cancer, you don't want that performance to drift because that could be catastrophic for the people involved. And that's the terminology that we use for that performance changing, drift. And there's two sorts. There's model or context drift and data drift. Model drift is where the purpose for which the model was designed has changed. So, for instance, you've got scammers sending emails, and the way that they send the emails, the text that they use, the style that they use, changes, and the model can no longer detect it. So you then have to retrain the model. And data drift, there was a case of this a little while ago for a high street bank that was using an AI for recommendations for loan applications. And then COVID struck, the pandemic. And the data that was coming in changed because of the furlough schemes where people had income, but it was different. So they had to completely retrain the model. They had to use a different data set. And then there's all the others. Accessibility, usability, security. And this is an interesting one because the data controls the behavior. A malevolent actor could manipulate the data in order to manipulate the behavior of the system. They call it poisoning the well. So what we have to do is try it. How does the system handle it? Mess with the data, see if we can get it to break. And if we can, they're going to have to change the way the model works. And then performance. But as I said, it's not just speed and volume. And then we've got some test techniques. Explainability is something that is required by law for systems that make decisions. And essentially, it has to be able to explain why it made that decision from the parameters. There are tools for that, and they can be embedded into the systems. But you can also use that for messing around to find out whether it's actually doing it right or not. And then we've got A/B testing. Again, very familiar. You put two up live, compare them, take the one you like. Parallel testing is where you've got the old system running alongside your new system. And you compare the outputs from the two, and then you switch to the new system when you're comfortable that it's working. Statistical analysis I mentioned. Exploratory testing. One of the key points that Tariq made this morning was that exploration is really important. That's what we're good at. That's what we should be doing, exploring. And AI is very fertile ground, especially generative AI, for exploratory testing. And use experts. If you've got an expert in the field that you're trying to emulate their behavior, use the expert to decide that. A real oracle. And then pairwise or orthogonal testing for reducing the number of combinations. This is old tech. Anybody in testing knows about this. But it's very effective for taking very high numbers of combinations of inputs and reducing it. So you can go from the order of 250,000 down to the order of tens of combinations. Then metamorphic testing. This is where we mess with the inputs and see how the output changes. Now this sidesteps the oracle problem because we're not interested in the values, we're just interested in the shape of the change. So if we change it up, does the output change up? If we change it down, does the output change down? And then I mentioned the adversarial testing. Model back testing is essentially taking the data from the old system feeding it into the new system, and comparing the outputs. So it's like parallel testing, only it's offset by time. Dual coding and algorithm ensemble is where you've got loads of different models, feed them all with the same data, compare the outputs. Coverage data, this one pretends to be coverage. It's not really. Basically what you do is you have a bunch of data that is designed to hit every single node or neuron within the network. Doesn't really prove anything. It's a bit like code coverage. It doesn't really mean an awful lot. And cross-validation is a good way of making sure that you've got good data. K-factor cross-validation technique is a really good one, where you take the data set that you're going to use, split it up into K number of chunks, and then you train it with all apart from one, and then test it with that one. Save the outputs, blank the model down again, do it again, only test it with a different chunk until you've done it with every single chunk and compared all the outputs from each of the runs. And then finally, affordances modeling, which is, it goes back to an old design technique. The idea that an object can define how it's supposed to be used by its form. So a mug has a handle, your cup has a handle on it, so you should grab the handle. That's the idea. And that has now been transposed into UX, where the idea is that the interface defines how you use it by its nature, so that you don't need instructions. It's a very Apple way of thinking, but you can use that within the UAT area. So that's all the testing tools. They fit into the quality engineering, into the life cycle. As Tariq mentioned this morning again, all the way through from the business case through to operation in live, the BAU. So that gives you the test tools, and I hope you can actually see where they fit in within the life cycle, the route to life. But then how do we assure that? That third one in the Holy Trinity, the quality assurance of the system. Well, at 2i, we've built our own assurance framework called Assure AI. And we think it basically comes down into 4 factors. So the accuracy, the robustness, the explainability, and the performance. And you should be able to see that in there are some of the things I've been talking about, that they slot in quite nicely. So data integrity, the model validation, and the continuous modeling, and the monitoring of the systems. And then you've got transparent algorithms and the explainability. That is explainability. That's the tool I was talking about. And then the performance. So you've got the drift and the modeling of that itself. So a lot of these fit into the framework. So if you understand how to test the AI and what can go wrong with the AI, you can build your own quality assurance framework for asking the questions of, have we done this? Have we done that? Have we done this? Do we have measures in place? Do we have metrics in place to make sure that that's happening throughout the length of the quality engineering lifecycle? And then from that, we give a rating. So rather than a RAG rating, because that can be a bit emotive, we use bronze, silver, gold, and not production ready. So from that, you can work out whether the system that you've got is being suitably assured, whether we're actually engineering quality in, and whether we need to move from the first stages of testing into the end-to-end, into the UAT. There's no point putting it live if half these are not production ready. And it's a nice, easy communication as well. This is easy, relatively easy, for C-levels to understand and for designers to understand. We can point to areas and go, your feedback loops aren't production ready. you need to implement better feedback loops. Or your security isn't, you need to implement better security. So there's a few resources and tools. There's loads out there now. It's changing so fast, I can't keep this slide up to date anymore. So I recommend that you basically use Google. If you want any of my slides, then please get in touch. I can be reached on LinkedIn through there or by email. And I'll be stood over in the speaker's corner afterwards, so if you want to come over and have a chat, please do. I also host a podcast called Quality Blether, which you can get on all good podcast sources. So please have a listen to that. It's where I get to talk to all these amazing people, like Andrew Bryan here. And pretty soon, Mike Jarrett. I enjoy it, so I hope you will. So, thank you.
No, Bryan, thank you. Let's start with the questions. That's what you need to do, and then you can also eat. Okay. What do you think, which is the level cap of the original testing pyramid an AI should do and not do?
That's an interesting question. I don't see why it shouldn't do any of the pyramid, but the question is, how do we make sure that it's doing it right? So if you get up to the UI level, it can do all the field validation and all that sort of stuff. It can generate Selenium tests or whatever you want in that respect, or Playwright. So it can do that. It can also do the API testing down at the bottom. If you're using contract testing, then that's great because you've actually got a definition of what it should look like. It should be straightforward. But again, you need a human in the loop. You need to make sure that what it's doing is good stuff.
Excellent. Okay, how can we distinguish between issues in the data and issues of AI representing the data? Yeah. It just switched, sorry. Now that's the question.
That's okay.
Yeah.
Again, this comes down to getting friendly with your data scientists. If you need to understand the data. The data is everything when it comes to AI systems. It's the most crucial part of all of it. So you've got to get to grips with that data science and get friendly with your data scientists.
Okay, I think it's the last question. Is there any case study related to AI application for safety critical systems like aviation or railways?
I have no idea. That's a very good question. I'm going to go away and search for some, see if I can find some.
I have to be honest, when I'm helping people how to be presenters on stage, this is the best answer that you can give if you actually don't have the answer. So thank you so much instead of, BSing. You're amazing. Big applause, ladies and gentlemen, for the last speaker before the lunch break. Thank you so very much.
Thank you.